Awesome. Thank you so much for that introduction. I want to say that this is not the longest co-author list I've ever been on. I'm from Arizona State University. We're a big research lab, so sometimes we have like 10 to 20 co-authors. Don't be surprised. So I'm here to present for all of my awesome co-authors this awesome work called MTSan, a feasible and practical memory sanitizer for fuzzing commercial off-the-shelf binaries. It actually misses 2 words right now on AR64. But it's OK. I'll mention why. So first, let's all appreciate fuzzing, because fuzzer is this amazing piece of software that generates and mutates test cases, feeds them into the target program, and waits for the target program to crash. Right? So why does the program crash? It's usually because the input triggers some unexpected or bad abnormal behaviors or abnormal conditions. Like, for example, you have a stack buffer overflow, and then you overflow the buffer on the stack, and then you overflow it all the way to stored pointer on the stack, or the return address or the stack canary on the stack, right? And then during execution, it may trigger a crash when the CPU tries to execute unmapped memory regions, or when the CPU meets like unsatisfiable conditions. Let's, for example, it assumes the stack canary is not modified before the function returns. So in this stack buffer overflow example, if the overflowing buffer does not overwrite any critical data on the stack, for example, then maybe there won't be any crashes, and then it becomes a problem for fuzzers, because when we're fuzzing, every time there is a bad behavior happen, we actually want it to crash, so that it becomes a good indicator for bad behaviors. So one solution to solve this problem for fuzzing and makes fuzzers more effective is applying sanitizers, right? So in this buffer overflow example, sanitizers can insert checks, and then those checks will be triggered as soon as there is even a 1 byte overflow. Let's say you're overflowing into the alignment between data structures on the stack. It's OK. The memory sanitizers will be able to detect them and then still trigger a crash. So let's take a look at how sanitizers work. I know our second awesome speaker today already talked about write zones. So if you don't remember it after 30 minutes, now let's revisit it. So one type of sanitizers are location-based sanitizers, right? So they rely on write zones, which are adjacent areas that are adjacent to variables that the write zones are protecting. And then these areas are inaccessible, right? So location-based sanitizers will raise alerts when these write zones are accessed at runtime, which means memory safety violations have occurred and are detected. So another type of sanitizers are identity-based. So they basically work by correlating memory pointers to the objects or variables that the memory pointers are pointing to. So identity-based sanitizers detect memory safety violations when pointers of object A are used to access object B, or simply accessing beyond the boundaries of object or variable A. So sanitizers are usually implemented as compiler passes, and this is mostly because the sanitizers will need information such as the types and sizes, boundaries of variables, and second, recompiling source code will allow these sanitizers to apply memory layout changes, program logic changes, and also try to optimize as much as possible, right, to reduce the overhead. Now the question is, what if during binary fuzzing, we don't have the source code for the original binary, for the original program? What can we do? How can we implement sanitizers? So we have a lot of great researchers in our area that have already proposed many binary sanitizers, but they all suffer from some common critical limitations. So the first limitation of the existing binary sanitizers is that they usually only support heap objects and can really only do very little for global or stack regions. So for obvious reasons, because boundary information is usually not available, right, for objects or variables that are on the stack or in the global memory region, without accessing debug symbols, for example. So the second limitation here is pretty obvious. Binary sanitizers cannot apply write zones to when they're sanitizing binaries. This is because write zones really require changing memory layout. Sure, you can do it when you're recompiling the source, but you cannot just recompile the binary code and reliably change all of the pointers, right? And this is really because all of these memory layout information has been lost during compiling. Another limitation, which is probably the most important one, is the runtime and memory overhead for binary sanitizers is usually very high. So without source code, a lot of optimizations that source-based sanitizers can apply, they no longer work. So such high runtime and memory overhead really reduces the fuzzing efficiency. And in fact, they're curtailing the application of these binary sanitizers on fuzzing. So while we were thinking about this problem, we had an interesting observation, and I will demonstrate it here with an example program that's correlated to CVE 2017-9047. So I know this is a pretty long program. I challenge you to find the bugs inside, but this is not the right time for it, so save time. Let's just focus our attention on the two boxes, right? We have two variables on the stack. One is called expert, the other one is called list. 5,000 byte long each. They're pretty big, So if you want to overflow any of them, you want to have a lot of bytes. And then to make overflowing easier, the program was actually calling struct one after another. Right? There's a series of structs called one after another. And then as long as, for example, your content name is long enough, you're going to overflow buff. And then buff was actually a variable that's passed in from the caller that was expert, the expert variable, right? So if you have more than 5,000 bytes, you're going to overflow beyond expert and overflow into list. That's the vulnerability. So during fuzzing, if the overflowing content is more than 5,000 bytes and overwrites all the way into the stack canary or the return address, then the program is very likely to crash. But if the overflowing content is less than 5,000 bytes, then it will only override part of the list variable without triggering a crash immediately, right? So if during binary fuzzing, we can infer the boundaries of expert and list on the stack, and we realize, each of them is 5,000 byte long. So we will then be able to detect this bug way before the fuzzer generates good input that requires 10,000 bytes in total that can overflow all the way into the stack canary. So two challenges. We need to figure out how we can recover memory objects in target binary without using source code information, right? Including what pointers are, which objects the pointers are supposed to be pointing to, the boundaries of the objects that the pointers are pointing to, right? And also the lifetime of these pointers and objects. The second challenge is how do we detect memory violations? Especially when we're fuzzing binaries with a much lower runtime overhead so that our sanitizer doesn't hurt fuzzing that much. So our intuition, access patterns can actually help us understand or infer data structures in memory, as has been demonstrated by Reverse and Howard that was published over 10 years ago. So in our example program, we can infer that there are two large char buffers, expert and list. They all exist on the stack, and when they're accessed through monitoring access, we know that they're both written during execution. So the key insight is that with normal input, right, you're writing to expert, writing to list, they're not overlapping. But when there's a bug triggering input case, a memory corruption happens, and the program will be writing across the boundary of expert and write all the way into the list. So we may infer that list and expert overlap on the stack, which is a conflict, right? So this is actually an indicator for memory errors that happen during execution. So to solve the second challenge of detecting memory safety violations at runtime with lower overhead, so we are using a new technique on hardware called memory tagging. So briefly speaking, memory tagging attaches unique 4-bit tags to pointers and bytes in memory. So when a pointer with a tag is used to access memory space with a different tag, the CPU will record it or just fault the access. So that way we can detect memory safety violations with much lower overhead due to it being hardware support, right? And also this is not only specific to AR64. Similar features also exist on other architectures, although our implementation is specific to AR64 with memory tagging extension. So here's our solution. It's called MTSan, which is short for memory tagging sanitizer. So MTSan rewrites binaries at runtime, infers memory layout using data access patterns that's logged during fuzzing, and then reports any memory safety violations found during fuzzing. So to address challenge 1, our key technique is called progressive object recovery. And to address challenge 2, the other key technique is called an RRR scheme, which stands for record, resume, and regression scheme. So we'll see how they work. So first, for progressive object recovery, It works by identifying object pointers based on how each pointer is derived. For example, if you have a stack pointer, if you have a stack object, you can access it from by using a stack pointer. You take the stack pointer, add an offset to it, right? You're deriving a pointer that you can use to access the object on the stack. So MTSan hooks heap allocators to track heap pointers and identifies stack pointers and global addresses during runtime. So MTSan then allocates a pointer to then allocates a tag to a pointer and all pointers that are derived from the same pointer. So the next step is inferring object boundaries. MTSan does so by watching the use patterns of tag pointers. So for example, if you have a pointer, you dereference the pointer at the byte offset 32. That means this pointer is pointing to an object. The object is at least 32 bytes long. So you can refer to our paper for a full list of rules, but honestly, the rules are pretty intuitive. So finally, because there are many executions during fuzzing, MTSan progressively refines the inferred object boundaries by analyzing every single fuzzing input, and then releases alerts in case any conflicts are observed. So this way, it allows us to detect the bug in our motivating example way faster before the fuzzer generates a 10,000 long byte string that feeds into the program. So when using MTSan to fuzz real-world programs, we found a problematic behavior. So that is because pointers that are derived at different program locations are treated as different pointers and they have different tags, but they can legitimately be pointing to the same object. Why? Because this is because compilers may very well be emitting multiple pointers for accessing the same object, especially for stack objects. Therefore, we need to handle this, right? Otherwise, we'll have a very high false positive rate. So we propose a technique called adaptive sanitization. In our motivating example, because the boundaries of X-brand list are all inferred by MTSan, we say their properties are presumptive, and any violations that only involve variables with presumptive properties are non-critical. So instead of raising alarms immediately when list was accessed by a pointer derived from Xpert, MTSan records this non-critical violation, resumes the execution, and puts the input that triggers the non-critical violation back into the fuzzing queue. So this way, we are essentially forcing the fuzzer to focus on the non-critical violations that we found. And then in fact, the fuzzers are very good at doing that. And then the fuzzers will be able to find will be able to expose true positives in the end. So because we do not have access to any hardware that implements MTE, we had to use instruction analogs for our evaluation. We leave details in our paper. So during our evaluation, we realized that MTE achieves the lowest runtime and memory overhead. As a result, it achieves the highest fuzzing efficiency among all existing binary sanitizers that are available. So we also noticed that during fuzzing, the record-resume regression scheme escalated 7 non-critical violations to critical violations for real-world CVEs, which shows RRR was really useful. Finally, we tested MTSan on real-world vulnerabilities. That the results show that MTSan is more effective than existing binary sanitizers, detects more memory safety violations on stack, and global variables with much lower false positive rates. So in conclusion, we present a feasible and practical hardware-assisted memory sanitizer, MTSan, right now for binary fuzzing on AH64. And the first author is Xingman Chen. Unfortunately, he's not here. If you're interested in the work, email him. And then soon we will be open sourcing the implementations. Thank you.